Hi, my name is Jamil, and today in this section we'll be looking at solutions of linear systems using row transformations. Our objectives will be to work with matrices and technology, to use matrix row transformations, to learn about row echelon method, reduced row echelon method, and some special cases. Matrices are especially useful for uses with computers and calculators, especially with large systems. However, it's important that we know some of the underlying methods that go into solving these matrices. Let's take a look at an augmented matrix. Here, what we see is a system of three equations, denoted a1x plus b1y plus c1z equals d1. Then the second equation, a2x plus b2y plus c2z equals d2. And then the third equation, a3x plus b3y plus c3z equals d3. Instead of keeping this written as an equation, we can rewrite this as an augmented matrix. Now, it's important that you keep the coefficients of all the variables in the correct place. The first column is the coefficients of the x's, so we put a1, a2, and a3. Then in the second column, we have the coefficients of the y, and the third column, the coefficients of the z. In the last column, we have the constants. It's important that you put the equation, the first equation goes across the top of the first row, second equation, second row, and then the third equation down the third row. And doing it this way, we can write the system as an augmented matrix, and then we can use row operations in order to help us to manipulate this matrix. So let's take a look at some of the steps to doing that. Matrix row transformations. For any augmented matrix of a system of linear equations, the following row transformations will result in a matrix of an equivalent system. First, any two rows may be interchanged. Second, the element of any row may be multiplied by a non-zero real number. Third, any row may be changed by adding to its elements a multiple of the corresponding elements of another row. So let's go ahead and take a look at an example using some matrix transformations. Here we're asked to use matrix transformations to transform the first matrix 1, 3, 5, 2, 0, 1, 2, 3, 1, negative 1, negative 2, 4 to the new matrix 1, 3, 5, 2, 0, 1, 2, 3, 0, negative 4, negative 7, 2. So what we really want to do is transform that third row into a new row. So starting with that original matrix, what we want to do is take the first row and subtract it from the third row. In doing that, what would end up resulting is the following. The top row would stay the same, 1, 3, 5, 2. The second row would be the same, 0, 1, 2, and then 3. But now it's the third row that we want to alter. So again, what I'm going to do is I'm going to multiply the top row by negative 1 and add it to the third row and make that my new third row. So multiplying the top row by negative 1, that gives me negative 1, negative 3, negative 5, and negative 2. And now adding that to the third row, 1 plus the negative 1 gives me 0. Negative 1 plus negative 3 is negative 4. Negative 2 plus negative 5 is negative 7. And then 4 plus negative 2 is 2. So the resulting matrix is the matrix that they asked us for. You can also use a graphing calculator to help you do operations like this. I've already taken the calculator and input the matrix that we were dealing with, and I've set up the row operation and went to the menu and pulled it up. And now by using the graphing calculator, it will come up with the exact same answer that we found, only much quicker. We can use matrix row transformations in order to put our matrix in something called row echelon form. Let's take a look at this form. Here you see the matrix put in row echelon form. Notice the bottom triangle of the matrix is all zeros, and then across the main diagonal we have ones. Going across, the form looks like 1, B1, C1, D1, then 0, 1, C2, D2, and then 0, 0, 1, D3. This is sometimes referred to as the triangular matrix, and it's very useful in helping us solve systems of equations. Let's now use row echelon form to help us solve this following 2x2 system. Here we're asked to solve the equations, the system of equations, 5x plus 2y equals 1, and 2x minus y equals 4. So the first thing that we need to do is write this as an augmented matrix. Taking our coefficients of the x's, we have 5 and 2, so that forms our first column. And then the second column will be the coefficients of the y's, which are 2 and negative 1. And then the third column are the constants, 1 and 4. And putting this in an augmented matrix gives us this as a result. Now what we want to do is use row transformations in order to write this as a row echelon form matrix. So we'll take that following matrix, and the first thing we'll do is we'll multiply row 1 times 1/5. Doing that, this matrix will now result in the following matrix. 5 times 1/5 is 1, then 2 times 1/5 is 2/5, and then 1 times 1/5 gives me 1/5, and then the second row will stay the same at 2, -1, 4. Now, in order to get to our row echelon form, what we need to do now is get a 0 in this bottom corner. In order to get a 0 there, what we're going to do is multiply the first row times the -2, and then add it to the second row. So multiplying that first row times the -2, I'll write it beneath, -2 times 1 is -2. -2 times 2/5 is -4/5. -2 times 1/5 is -2/5. And now what we want to do is we want to rewrite this matrix, keeping the top row the same, 1, 2/5, and then 1/5. But now we want to add this new row to the bottom row to create the new bottom row. So 2 plus the -2 gives us 0. -1 plus the -4/5 is really -5/5 plus -4/5, and that's -9/5. And then 4 plus the -2/5 is really 20/5 plus -2/5, which is 18/5. Let's now go back and make sure that we have 1s on the main diagonal. What we need to do now is take that second row and multiply it by a -5/9 in order to get a 1 in this position. So, transforming this, what we'll do now is we'll keep the top row the same, and that'll be 1, 2/5, and then 1/5. And now we'll multiply the second row by -5/9. So that will stay as 0. -5/9 times the -9/5 will give us a 1. And then the -5/9 times the 18/5 would give us a -2. So now that we've got the row echelon form, what we can do now is transform this back into a system of linear equations. So keeping in mind that the first column is for x's and the second column for y's, and the third column is the constants, this top row becomes 1x plus 2/5 y equals 1/5, and the second row becomes 1y equals -2. And there's the advantage of the row echelon form. Right away we see that y is equal to -2 in this system. So to find the value of x, all we need to do is take that -2 and substitute it back into the other equation. That would give us x plus 2/5 times our y value of -2 is equal to 1/5. X, now multiplying this out, we have a -2 times 2/5, which is a -4/5, equals 1/5. And then adding 4/5 to both sides, we find that x equals 1. So our solution for this particular system of equations is the point 1, -2. Let's now take a look at a system that uses 3 variables. Here we're asked to solve the following system. We have x plus y minus z equals 6, 2x minus y plus z equals -9, x minus 2y plus 3z equals 1. Now what we're going to do is we're going to write an augmented matrix, and we're going to use the coefficients of the x to be the first column, so it'll be 1, 2, 1. The coefficients of the y for the second column, 1, -1, -2. Coefficients of the z for the third column, -1, 1, and 3. And then the constants for the constants for the last column, which would be 6, -9, 1. So our matrix will end up looking like this. Now, once we've got this matrix, we need to get into row echelon form. So the first thing we're going to do to start this is we're going to take and try to get zeros in these two positions here. So one way to get a 0 in this position would be to multiply the top row by -2 and then add it to the second row. So if I multiply that top row by -2, I'll write it down here below the matrix. It'll become -2, -2, 2, and -12. Now, keeping the top row the same, we'd end up having 1, 1, -1, and then 6. And now adding -2 times the first row to the second row, here's our matrix down here, our row down here we multiplied by -2. So adding this to the second row, 2 plus the -2 gives us a 0. negative 1 plus negative 2 is negative 3. 1 plus 2 gives us the 3. And then negative 9 plus the negative 12 gives us a negative 21. And we've succeeded in getting a 0 in this position. Next, what we want to do is we want to get a 0 in this position. So this time what we'll do is we'll subtract the top row from the bottom row. And that will result in a 0 here. So 1 minus the 1 from the top row gives us a 0. Negative 2 minus the 1 from the top row gives us negative 3. And then 3 minus the negative 1 gives us 3 plus 1, which is 4. And then 1 minus 6 gives us negative 5. So here's what we get when we do our first two row transformations. And you can see we have zeros in both of these locations. Now what we want to do is we want to try to get a 1 on the main diagonal in this location. So in order to do that, we're going to multiply the second row by negative 1/3. Keeping the top row the same, we have 1, 1, negative 1, and then 6. Multiplying the second row by negative 1/3, we get 0. And then negative 1/3 times negative 3 gives us the 1 we're after. Negative 1/3 times 3 gives us a negative 1. And negative 1/3 times negative 21 gives us a positive 7. Now, instead of copying down the third row, I'm going to do another row transformation here. What I want to do is I want to make this location into a 0. Now, the easiest way to do that without affecting the 0 we already have is to make use of this new row we've just created. So what I want to do is I want to multiply this new row by positive 3 and add it to the bottom row over here. So multiplying this row right here by positive 3, I'll write it underneath. Positive 3 times 0 is 0. Positive 3 times 1 is positive 3. Positive 3 times the negative 1 is negative 3. And then positive 3 times 7 is 21. So to create the new third row, I'll add these two rows together. 0 plus 0 gives me the 0. Negative 3 plus positive 3 gives me a 0 that I need in this location. Now you can see the triangular matrix starting to form with zeros in the bottom corner. 4 plus negative 3 gives 1. And then negative 5 plus 21 gives us 16. Now what you can see is that we have the row echelon form. We have a 0 everywhere in the bottom triangle, and we have positive 1 everywhere along the main diagonal. So now what we can do is we can transform this back into a system of linear equations. The first equation is x plus y minus z equals 6. The second equation is y minus z equals 7. And then the bottom equation is z equals 16. So now that we know these facts, we can go back and substitute into each of these equations to find the actual values of x, y, and z. So again, to remind you, we've got the equations x plus y minus z equals 6, y minus z equals 7, and then z equals 16. So using the fact that z equals 16 in the equation right above it, we get y minus 16 equals 7. And now adding 16 to both sides, we get that y equals 23. So now we've got z is 16, y is 23. Taking these two results and substituting all the way back into the top equation, we get the x plus our y value of 23 minus our z value of 16 has to equal 6. Well, x and then 23 minus 16 is positive 7, and that equals 6. So now subtracting 7 from both sides, we get that x equals negative 1. So our solution for this system would be the point negative 1 for the x value, 23 for the y value, and 16 for the z value. And that would be the solution for that particular system of equations. Here's a slight variation of row echelon form called reduced row echelon form. Now the advantage of this is that we have zeros in the lower triangle as well as zeros in the upper triangle and ones everywhere on the diagonal. If you can get your matrix to be in this form, it's easy to read your solutions because the value here will be the answer for the x, the value here will be the solution for the y, and the value here will be the solution for the z. Let's go ahead and take a look at this next example where we'll be using reduced row echelon form. Here we're asked to use a graphing calculator with reduced row echelon capability to solve the following system. we're given x plus 2y plus z equals 30, 3x plus 2y plus 2z equals 56, and 2x plus 3y plus z equals 44. Now, the first thing you'll need to do is make sure that you write down your augmented matrix correctly. So I'll take you through that really quickly, and then we'll go to the calculator. So in order to put this in our augmented matrix, remember the first column is the coefficients of the x. So that's 1, 3, and then 2. Second column are the coefficients of the y's, which is 2, 2, and 3. Third column, coefficients of the z's, 1, 2, and 1. And then the last column is the coefficients, or I should say the constants, or the answers, which is 30, 56, and 44. So that would be our augmented matrix. Now, what we need to do is go to the calculator that can do reduced row echelon form. So here on this calculator, we can see that option B down at the bottom of the screen is RREF, which is reduced row echelon form. So selecting that and then going to get the matrix, which I've already entered in and called matrix A, and then hitting enter, we can see that very quickly it returns the answers. You can see the upper and the lower triangles are all zeros and one's on the main diagonal. So the solution for this particular example is that x is equal to 8, y is equal to 6, and z is equal to positive 10. Now, what we want to do now is take a look at what an augmented matrix will look like if our solutions are dependent or inconsistent. So let's look at some of these special cases. Special cases. Here you see a matrix that has 1, 2, 1, 4 is the first row, 1, negative 2, 3, 1 is the second row, and then 0, 0, 0, A is the third row, where A is not equal to 0. If you should come across a matrix that has entries in your first two rows, but a row of zeros, and then a non-zero value here, this particular system will be an inconsistent system, and there will be no solution for this particular system. Let's look at another special case. Here in this augmented matrix, we have the first row 2, negative 5, 3, 1, 1, 4, negative 2, then 8, and then a row of zeros going all the way across, including the last entry being 0 as well. If this should ever happen, then this will be a dependent system, and what you'll find is an infinite number of solutions, and you can write them as a solution that depends on one of the variables. In this section, we learned how matrix row transformations can help us solve systems of linear equations. You should practice by doing the exercises in your textbook, and I'll see you next time.